All right, so we're going to dive right into section 6.4. Goals of section 6.4 are describe the sequence of transformations that map one figure onto another congruent figure. We've been doing that almost this entire time, not really mapping one onto the other, but we've been dealing with transformations involving congruent figures because every transformation we've done up to this far have been rigid transformations, and they all result in isometric transformations. They all result in maintaining distance or preserving distance, and therefore are all congruent, resulting in congruent figures. Right, so we're just going to focus on congruency in this lesson. And this kind of sounds like Groundhog Day, but you're going to be drawing an image given the pre-image and a sequence of the transformations on the coordinate plane. So pretty easy stuff here. We're just going to be focusing a little bit on congruency. All right, so we have an image. We're going to say that this is a triangle FGH. I'm going to call it triangle red. Right, triangle red here. It's on graph paper and it's rotated on the graph paper, and move it to the right. Sounds a lot like a clockwise rotation and then a translation. Right. Explain the method she can use to determine if each side of the triangle has the same length as the triangle that she had when she moved it. Well, of course it's going to have corresponding lengths because she didn't actually, change the triangle or on the paper. She literally just rotated this piece of paper. Like, this is a piece of paper, right? Better select it bigger. This is the piece of paper. She rotated it clockwise like that. Make this transparent. All right, she rotated clockwise like that, and then she moved it over. That's literally what she did, right? So, of course, they're going to be the same measure, right, for each side. So that's what she can do. She can do what I just told you. She can overlap it, right, on the piece of paper, slide it over, overlap it, and then she can see if the each lengths are coincide with the proper lengths. So she can make sure that, I guess I can show that again, huh? She can make sure that rotate this clockwise 90 degrees, and she can make sure that F and G are the same lengths. Segment F and G is the same length. Segment HG is the same length, and segment FH is the same length. That's what she can do, right? So how do we put that? Well, we'll just write it up here. I'll write it in red. She can rotate. I'll make that bigger, huh? Yeah, like 14 or 16. Rotate and slide the graph paper over over the oh wait, it's the same graph paper. Okay, so she can't do that. All right, so she can use a ruler. She can use a ruler to measure each side, or she can use patty paper to capture each image, the sides. I mean, so that there you go. That can be your answer right there. Okay, it's kind of a silly question to me because you're not actually changing anything. Okay, in this case, it would be literally the same piece of paper. It's a silly question. All right, and then explain what method she would use to determine if each angle would be moved. Right. So you could use a protractor, right? She could use a protractor, like measure each angle. And then when she flipped it and moved it, she could measure the angles again. So she could use a protractor. Or a compass for that matter. Before and after the movements. Change. Or you can use patty paper. Before would also suffice. You could check the patty paper. You could record the image before, and then move it, and then record the image after. But again, it seems a little silly to me since you're not actually just moving it. Why would it change anything? Okay, so explain why showing that the lengths, the side lengths, and the angles have the same measure shows the transformation can be used as isometry. Well, you defined isometry or rigid motions. Isometry is defined as when the angle measures and the AS measures me EASURM and side lengths and the lengths of the sides remain the same before and after the transformation. E congruence, the pre-image and image, pre-image and image are congruent because that is the definition of congruence. Okay, so there we go. That is my my answers to the first couple of ones there. Okay, so let me see if I can pull up the next couple. Where is the next couple? Oh, that's not it. That is not it. There's the window I need. There is the window that I need. This one. Okay. 4, 5, and 6 next. Copy right over top of this. Now let's Control Alt delete, and put right over top of that. All right. All right. Explain the methods that can be determined. Oh wait, that's more than I copy. Bear with me. Thank you very much. Okay, here we go. That's better. All right. All right, we got 2 line segments and a point. We got TN is a line segment, despite the fact that there's no little line over top of TN like it's supposed to be. It's a line segment. And that's TN. Line segment TN. And line segment T prime N prime. Like that. Are shown on the grid. The point A is shown on the grid. Point A green. Point A being green. A is going to be green. Yeah, A is going to be green. Okay, draw T prime. Okay, so that's the angle we're going to draw. I want to make that green. Doesn't need to be as fat though. Maybe something like that. That's the angle. It looks like we're going to do a rotation here. I bet. That's a 90-degree angle. I'm just guessing though. Okay. Describe the transformation that was applied to make T. Yeah, it seems to be a 90-degree rotation, I bet. Right, because yeah, well, first describe the label the angle measure. Oh yeah, I got label the angle measure. I must skip one there. Label the angle measure. It says 90 degree. I'm gonna label it like this. I'm gonna label it like this. Like that. It's 90 degrees. It bothers me. Gonna go wonky. It'll stay wonky. Okay, it's gonna go like this. 90 degrees. That's my 90-degree angle. Okay, it's 90 degrees. Okay, so describe the transformation applied from Tn to my blue to my red to my blue. All right, so this is going to rotate 90 degrees and looks like it's going to rotate clockwise. So it's rotating. Oh wait a minute. Rotating. N is here, and T's here. Right. So if it's gonna N's gonna end up this way, this has to rotate counterclockwise. This has to come down. This has to come down this way. Like that. So that's going to be a clockwise rotation, a counterclockwise rotation of 90 degrees. So this is a counterclockwise rotation of 90 degrees. 90 degrees, because that would put the T, down here, right? So that makes it look like something like this. After I did that, it makes it look something like that. And that would be like pretty parallel. Like that-ish. Okay. And that would be N prime and T prime. But there's I think it would move over a little bit too after it was rotated. But got to complete the statement here. It's a rotation about point A, by the way. Gotta add that little detail about point A. Point A. Okay, and they got a point thing here. There is a blank between the sets of point T. Oh, the sets between. There's a blank between the set of points between on the line segment and the other line segment. Therefore, the points on the line segment must have. Okay, all right. So there is isometry, or isometry. Yeah. So this is saying, hey, everything on all the points on this are isometric to all the points on this. So everything on this matches everything on this, right? So this is isometric. There is isometric. Isometry between all of the sets, all of the set of points, because there's an infinite amount of points on this line segment, because points don't have any dimensions, right? So there is an isometry, there is isometry between the sets of points on Tn and the sets of points on Tn prime. Therefore, all the points on Tn all the points on P prime and prime match. That should be blue, but I don't care. All right, so that is that one. Okay, moving on to the second page. Okay, let me move that out of the way so I can grab the next couple ones. Okay, probably grab the whole. This. Let's delete it on that. And grab the first two. Go like in between. Well, not much where I will grab this. Whole thing. Okay, all right, so we got three quadrilaterals, BWR, the prime of BWRY, and the double prime of that one. Okay, this one is going to be red. My initial one's going to be red. No, that's the initial one. This is my initial one. That's my initial one. Next one's going to be blue. The prime one's going to be blue. And well, I went to other lines. I'm going to stay in the lines. And green, my third one. That's my green one. So green, red, and blue. Nope. Blue. That was red. Red and blue. Okay. Here's shown on my grid. First, second, third. Original, first transformation, second transformation. That looks like a rotation. Okay. Describe the movements that should be done with patty paper. Copy the quadrilateral. And so that it lays on top. Okay, well, I don't have patty paper, but I can copy and paste stuff. Okay, so let me grab my select button. Let me copy and paste this thing like it's going to be on patty paper. And paste it. Make it transparent again. Oh, it was transparent. Now it's transparent again. That's not transparent. Come on, give me something transparent here. It's transparent selection. See through the transparency. What's going on? Come on, man. Transparent selection. Transparent selection. Whatever. Okay. Okay. So describe the movements should be done on patty paper with a copy of the quadrilateral so that this red overlies blue. All right, so red overlies blue. Red overlies blue. All right, well, this is the line. This is the line. This line right here is the line. X
is the line x equals negative y. So every time x goes over 1, y goes down 1. That's why it's x equals negative y. Or you could say it's y equals negative x if you're going backwards. So every time, or y equals negative x. Yeah, because every time y goes up, x goes back 1. Whatever way you want to look at it. Okay.
So, yeah. So if I were to figure out what this was, well, let me see what happens if I rotate this thing. It's not a 90-degree rotation. Let's see if I rotate it 180 degrees. Nope, that doesn't match. Let's see what happens if well, flip it vertical won't match. I bet this is a since they just happened to give me this line right here. I bet it's a rotate about about that line. I can verify that because it would be a negative x, negative y. Let's see, my x is 1, my y is 2. That means it would be negative. My b prime would be negative 2 and 1. Negative 1, and it is. That's the relationship. Yep, so that's a reflection across the y equals negative x line, right? So that's what that is. Okay, if I had patty paper, I could rotate, I could flip it, and you'd show it. I can't flip it in that direction, right? But I can show you, I guess, with the coordinates I just used. So my red coordinates are for B, where x equals 1, y equals 2. My blue coordinate was for B prime. My B prime was negative 2 and negative 1. So I looked at how they combined to each other. It was in the terms of blue, but the red value in my y term flopped, but it was negative, and my x term flopped, and it was negative. So x comma y pulls from negative y comma negative x is a reflection across the x negative y. And that's how I knew that. Okay. And then the going from blue to green. Well, that's a reflection, or that's an obvious translation, right? So if you look at that translation, I guess I could have done this if I had done a reflection across the x, like a reflection like rotate, flip vertically, and then I flipped it horizontally. That didn't work. Maybe if I flipped it, rotated it like that, and maybe I flip it, rotated it. I gotta flip it. There we go. Now that's okay. Now if I'm like this is an obvious rotate or translation. This is a translation over. So my x value is going to be negative and my y value is going to be positive. Okay. So by what magnitude? I look like it was on x. Okay, my delta x is 2. It looks like it's going to be from here to here. All right, so negative 3 to negative 7. My delta x is negative 4, or left
4 units. Yeah, and then my B is going to be -1 to 4. That's 5 units up. Or delta Y is +5 units. Or 5 units up. There we go. That's if I would have used my patty paper. If I could see through that, that would have been better. All right. The transformations used in both sequences. Let's see. They're all isometric. Right? Because the points, all the points of can be mapped. All of them can be mapped. All of them can be mapped. Use definition of congruence in terms of rigid motions to show how everything is congruent. B to B, W to B to Y, and then this to this and this and this and this and this and this congruent. So that one little point, you have to make sure that everything's in line properly. B, W, R, Y, B, W, R, Y, right? These can't be flopped around at all, right? Because B and W, BW, segment BW, BW, and BW are congruent, right? RY, RY, and RY are congruent. Right. I don't know what that is. W, RW, RW are congruent. If you get them out of order, the angles get out of order too, and it might not make sense, right? So you got to make sure that that stuff is all in the right order, and these might change letters. That's what 4.8 is all about. So you got to make sure that those are in the right order. Okay. All right. So use the definition of congruence of rigid motions. Okay. Well, the definition of congruence. Let's see. Use definition in terms of rigid motions to explain how both the sequences of quadrilaterals resulted. So BW, B, B, W, R, Y, and the corresponding primes maintained the angles and angle measures, line segment lengths the same before and after each transformation. Therefore, all of the quadrilaterals are congruent. There we go. That's what I'm putting. Let's see. As a result of the rigid transformation. There we go. That's words. There you go. That is the lesson for today. Hope that helped.